Hi, welcome to this presentation on the development of carbon capture and storage, or CCS, in India. This presentation is based on a critical review conducted by Rohit Shaw and Professor Soumyajit Mukherjee, published in the journal Carbon Capture Science and Technology in the year 2022. In the next few minutes, we'll explore what CCS is, why it matters globally and for India, what research has been done so far, and where India stands in terms of implementation. This is an important topic as India works toward balancing development and sustainability. CCS is a rapidly advancing subject, and it is recommended that the viewers also go through the latest publications to get absolutely up-to-date information on the subject. Let's begin with the basics of CCS. Carbon capture and storage, or CCS, is a climate mitigation technology that captures carbon dioxide emissions from industrial and energy-related sources and stores them so they don't enter the atmosphere. It plays a crucial role in helping countries meet their carbon reduction goals, especially those heavily dependent on fossil fuels, like India. This presentation will review both global progress and India's specific research, challenges, and opportunities in deploying CCS. It's based on a comprehensive study that critically analyzes India's geological capacity, R&D initiatives, cost analysis, and integration with climate policy mechanisms like the Clean Development Mechanism. Let's first understand what CCS involves at a technical level. Carbon capture and storage is a three-part process designed to reduce carbon emissions at the source. The first step, capture, isolates CO2 from flue gases in power plants or industrial facilities. This is often the most expensive and technically complex part. Next, the captured CO2 is transported, typically through pipelines, to a suitable location. Finally, the CO2 is injected deep underground into geological formations like depleted oil fields or saline aquifers, where it is stored permanently. Some variants of CCS also include using CO2 for beneficial purposes like enhanced oil recovery or converting it to stable minerals. Let's explore why this process is so important globally. CCS is not just another green technology, it's considered essential in almost every pathway that leads to limiting global warming to 1.5 degrees Celsius. It is particularly crucial for sectors that are hard to decarbonize, such as cement, steel, and thermal power. CCS allows continued use of fossil fuels with minimal emissions, making it a practical transition technology. It also supports energy security for countries like India, where coal will continue to play a major role in electricity generation for the foreseeable future. Globally, CCS is already being used in countries like Norway, the US, and Canada. India can learn from these examples while building its own capacity. This technology is crucial in the global effort to mitigate climate change by capturing carbon dioxide emissions from large industrial sources and storing them safely underground. Countries around the world are developing CCS facilities to reduce greenhouse gases and meet net zero targets. India, being one of the top emitters, has a significant opportunity to deploy CCS alongside renewable energy to ensure a sustainable future. India is facing a growing challenge in balancing its energy needs with environmental commitments. With coal being the primary source of electricity, the country contributes significantly to global CO2 emissions. Industrial clusters in states like Gujarat and Maharashtra are major hotspots. To meet its climate goals, India must integrate CCS technologies in these high-emission areas while continuing its shift toward renewables. The CCS process consists of three main components: capturing carbon dioxide at its source, transporting it through pipelines or other methods, and then storing it in underground geological formations. Each stage requires specific technologies and infrastructure. Understanding how these components work together is key to implementing a successful CCS strategy. There are several types of carbon capture technologies. Post-combustion capture is the most common, where CO2 is removed from flue gases. Pre-combustion involves gasifying fuel and separating CO2 before combustion. Oxy-fuel combustion burns fuel in pure oxygen to produce a CO2-rich stream. Chemical looping uses metal oxides to indirectly combust fuel. Each method has its own advantages and challenges. Transporting captured CO2 is a critical component of the CCS chain. Pipelines are considered the most efficient mode, but India lacks a dedicated infrastructure for CO2 transport. Setting up a regulatory framework, acquiring land for pipelines, and ensuring safety standards are challenges India must address. Developing a national transport network will be crucial to link emission hubs with suitable storage sites. India's diverse geology includes over 24 sedimentary basins that can be used for CO2 storage. These formations, such as Bombay and Krishna Godavari, have characteristics suitable for long-term containment. Saline aquifers and depleted oil fields are especially promising due to their capacity and accessibility. Proper site selection and risk assessment are essential to avoid leakage and environmental hazards. The Ankaleshwar oil field in Gujarat serves as a key example of using CCS for enhanced oil recovery. By injecting CO2 into the reservoir, oil production increases while simultaneously sequestering CO2 underground. This dual benefit makes CO2 economically attractive and technically feasible. India can scale similar projects in other mature oil fields to jumpstart CCS adoption. Coal seams, especially in the Gondwana basin, can be used to store CO2 while enhancing coal bed methane recovery. When CO2 is injected, it displaces methane adsorbed in the coal, which can be collected as a fuel. Simulation studies show promising results, but real-world deployment will require careful analysis of coal permeability and gas dynamics. Deep saline aquifers in the Ganga basin are a major opportunity for storing CO2. These aquifers are typically brackish, meaning they are not used for drinking or irrigation, making them ideal for sequestration. Geochemical simulations indicate that CO2 can be safely stored in these formations for hundreds of years. The Dharwad Greenstone Belt in Karnataka is composed of ultramorphic rocks that can naturally react with CO2 to form stable minerals. This process, known as mineral carbonation, is highly secure and permanent. Using such rock formations for carbon storage is a promising pathway for long-term climate mitigation. In northern India, particularly in Nainital, agroforestry systems using poplar trees have demonstrated effective carbon sequestration. These plantations not only capture CO2 but also provide economic returns for farmers. Expanding such land use practices can support India's mitigation goals and rural development simultaneously. India's research landscape in CCS is expanding through national programs and international collaborations. Institutions like BHEL and IIT Bombay are leading projects on MOFs, algae-based capture, and simulation of capture processes. Strengthening R&D will be key to developing cost-effective CCS technologies tailored to India's needs. The cost of CCS remains a significant barrier to its widespread adoption in India. Most of the cost is associated with the capture stage, especially in retrofitting existing plants. Developing low-cost materials and processes, and introducing carbon pricing, will help overcome financial hurdles. India has taken initial policy steps towards CCS through international programs and voluntary funding. However, there is no formal regulatory mechanism or subsidy scheme for CCS in place. Inclusion of CCS in emission trading schemes and clean energy obligations would encourage adoption across sectors. CCS faces environmental and social concerns such as leakage risks and land use disputes. Despite low probability, public fear of CO2 storage can delay projects. Transparent stakeholder engagement and environmental monitoring are essential for gaining public trust. CCS can complement renewable energy by offering stable, dispatchable power. While solar and wind are expanding rapidly, fossil-based power with CCS can help manage base loads. This hybrid approach will be essential in achieving India's renewable energy targets without sacrificing grid stability. India's CO2 emissions are expected to reach over 5 billion tons by 2030. CCS offers a way to reduce emissions from sectors like cement, steel, and refining, which are difficult to decarbonize otherwise. Immediate action is required to meet global climate commitments and domestic environmental targets. India's CCS roadmap envisions a phased approach, pilot projects by 2030, scaling up by 2040, and integration across sectors by 2050. Success will depend on policy, funding, infrastructure, and public-private partnerships. The roadmap also emphasizes geological surveying and international collaboration. Global CCS projects like Sleipner in Norway and Boundary Dam in Canada offer valuable insights for India. These projects demonstrate that large-scale CO2 storage is feasible and safe when done correctly. India can adapt best practices and avoid pitfalls by studying these international models. To summarize, CCS is essential for India's transition to a low-carbon future. It allows continued economic growth while reducing emissions in key sectors. With proper investment, policy support, and public engagement, India can become a global leader in CCS technology. Thank you for your time and attention throughout this presentation. I hope this discussion helped you understand the importance of carbon capture and storage, especially in the Indian context. CCS is a rapidly advancing subject, and it is recommended that the viewers also go through the latest publications to get absolutely up-to-date information on the subject.